So welcome everyone to the lecture number 8 in the Mathematical Statistics in the winter term 2023-24. I start with a repetition what we did the last time. Last time we considered the kernel density estimator and showed the result about the weak universal consistency of this kernel density estimator. This was theorem 3.3.4, which you can see on the slide here. So you have IID random variables x1, x2, and so on, and they have a density f with respect to the Lebesgue-Borel measure. You let fn of x be the kernel density estimate applied to the sample x1 to xn of x. So fn of x is 1 over n times hn with exponent d times sum I equal 1 to n k of x minus xi divided by hn, where k is the naive kernel, so k of u is the indicator function of the unit ball around 0 in Rd, and normalized such that you divide by the volume of this unit ball, so this is a density because it integrates to 1, and hn greater 0 is the main parameter of the estimate, it's the so-called bandwidth. And the bandwidth satisfies hn tends to 0 for n tending to infinity, but not too fast, in the sense that n times hn to the power d tends to infinity. And then we have seen that the L1 error of our kernel density estimate, the integral of our absolute value of fn of x minus f of x dx, converges for sample size tending to infinity to 0 in probability, regardless what the density f is. So for each density f, which you can think of, if you generate IID data according to this density and use it to estimate the density estimate by the kernel density estimate, which satisfies these conditions here, then the L1 error goes asymptotically to 0. And as a corollary, we have seen that we can estimate in this situation where we have a density, we can estimate the distribution of our sample consistent in total variation distance, because if we just use as a standard distribution estimate, the estimate which we get if we replace in the probability of some set b is the integral over b of the density of f of x dx, the density by the kernel density estimate meter. So our estimate mu n hat of some set b is integral over b fn of x dx. Then the supremum over all Borel sets b in Rd of absolute value of mu n hat of b minus mu of b converges to 0 in probability for every distribution which has a density with respect to the Lebesgue-Borel measure. And what we proved today is we sharpened this theorem 3.4. We showed it under the assumption of theorem 3.4. The L1 error converges even almost surely to 0 for every density. And that's the first part which I do. That gives us theorem 3.6. About a strong universal consistency of the kernel density estimate. So strong universal consistency of the kernel density estimator. Under this assumption of theorem 3.4, so you have this IID sample of your distribution, you have the kernel density estimate made up with bandwidth hn and with naive kernel, and the hn tends to 0 for sample size tending to infinity, and n times hn to the power d comes to infinity. We even have the L1 error again, n of x minus f of x, integrated over whole RD, absolute value of it, goes to 0 not only in probability but even almost surely. Move this away. Again, it's a universal consistency, so for every density. And this is a result which we prove by using the previous result about convergence in probability. In fact, in the proof you have seen that even the expected L1 error goes to 0, but that's equivalent to the conversion in probability, because the conversion in L1 implies the conversion in probability, and if you have conversion in probability, then by Jeffet you know that this one is less than 2 times integral over f of x minus n of x plus the x, which is less than 2 times the integral over f of x dx, which is less than, or which is equal to 2, because f is a density. So this is a bounded random variable, and if you have almost sure conversion, then you can conclude from, if it's a bounded random variable, from the dominated convergence theorem, that it also converges to 0 in expectation. But this is also true if we just have conversion in probability, because the conversion to 0 of the expectation, that's a conversion of a sequence of real numbers, and the conversion of sequence of real numbers to 0 is equivalent that for every subsequence of the sequence, you have a sub-subsequence which converts to 0, and then you take an arbitrary subsequence of this original sequence. This subsequence converges, of course, also in probability to 0, because the original sequence converges to 0 in probability, and then for the subsequence there exists a sub-subsequence which converges almost surely. And then you can apply the dominated convergence theory to this thing. So we know that under theorem 3.4 the expectation of this one goes to 0, and now we just proved that the random L1 error minus its expectation goes to 0, and for this we use the next theorem, the theorem 3.7, the inequality of magnetic diameter. And it's a concentration inequality. It makes some statement about how the random value deviates from its expectation in a special situation. And the special situation is the following. You have independent RD-valued random variables Z1 to Zn. So let Z1 to Zn be independent random variable, RD-valued random variables. And they take values in some measurable set, a subset A of RD. Then you have a measurable function from a to the power n to r. I call this f, and assume that this measures function satisfies if you look at f at some points x1 to xn, and then you keep all the points the same, but you change the point at position I, you replace xi by xi prime, then the function values changes at most by some constant ci, and that's the assumption that the supremum over all absolute value of f on z1 Zn minus f of z1 z I minus 1 zi prime zi plus 1 Zn, this guy, where z1 to Zn and zi prime are values in A. This deviation is less than some constant Ci. For some constant Ci, which is of course non-negative, and all I equal 1 to n. And then we look at the random variable f of z1 to zn. We are plugging the random variables capital Z1 to capital Zn instead of the deterministic values small z1 to zn in star. And consider what is the deviation between this random variable and its expectation, and give bounds on that. And the statement is then we have for every epsilon greater 0, z1 to zn minus expectation of f of z1 to zn. And this probability is greater than epsilon. And the statement is this is less than e to the power minus 2 epsilon squared over sum I equal 1 to n ci squared. And the same if you look in the deviation, not in the from the expectation to the right, but also from the expectation to the left. So if I look at the expectation of the probability that the expectation of f z1 to zn minus if random variables is greater equal than epsilon, that's also less than this term. So this is a statement about the concentration of a random variable around its mean. And this random variable has a special form. You use independent random variables, say z1 to zn, that don't have to be identically distributed. And you plug them in some function, real value function f. And if you just change one coordinate, then the change should be a closed set. Do you know some similar inequality already? Remember from probability theory? Does this remind you to anything? Have you ever seen some inequality where the random variable minus its expectation, greater equal epsilon, is less than some exponential term? Have you ever seen two inequalities where the random variable minus its expectation is less than exponential term? Yeah. Any idea?
Yeah, I'm thinking about the names.
Höfting and Bernstein. There's a Höfting and there's Bernstein. Bernstein, you have IID random variables, so this is more of a Höfting type. And in fact, if you use that f of z1 to zn is just the sum of the z1 to zn, then this is exactly the inequality of Höfting. Because in Höfting you have that the z, this implies the inequality of Höfting, because in Höfting you have that the zi take on values in some interval from ai to bi. So if I change the zi here in the sum, then the whole thing will be, the maximum difference will be bi minus ai. So ci is bi minus ai. So I have the probability that the sum of the zi's minus the sum of the zi's minus the expectation of the sum greater or equal than epsilon, which is the same then, Höfting is formulated in that sense that the arithmetic mean of the zi minus the expectation of the arithmetic mean is greater or equal than epsilon divided by n. Then you plug in here epsilon divided by n, and for the ci you plug in bi minus ai, then you get exactly the inequality of Höfting. And in fact, as you will see, we will also use a similar proof. It's based on Journal of Exponential Bounding method again. And you make an exponential, derive an exponential bound with some technical proof. Question? Please.
The left side is supremum. The supremum is for all z1 to zn and zi prime that we choose, right?
They are possible. The supremum is for all z1 to zn, zi prime that are, well, okay, that can occur. Because the random variables takes on values in this za, yeah? And then supremum for all, over all values which can occur for the random variables. If you change one of the random variables. Okay? Okay, what I do next is I prove theorem 3.6 using theorem 3.7, and then we prove theorem 3.7. So it's a clear plan what to do. To prove theorem 3.6 by using theorem 3.7 is one of the list of my exams question. It's one of the questions on the list of my exam questions. So again, I can prove it with, or I should prove it without looking in my notes. And we start with that. And in this exam question, the inequality of McDiarmid will be given. You know this one, but you have to formulate the proof or the result about the strong consistency of the kernel density estimate. So proof of theorem 3.6. I first need a notation for the kernel density estimate, and this is fn of x, x1 to xn. Let fn x, x1 to xn. Yeah, I didn't want to start with this one, sorry guys, but I do it anyhow. To add k of x minus xn. What I really wanted to do, I want first to explain what I will show, but instead we first use the notation. And then I have a g, that's my L1 arrow. G of x1 to xn, that's integral over f of x, x1, fn, x1, xn, minus f of x, dx. And we want to show g of capital X1 to xn tends to 0 on G. And the first thing is, what do we know? That the expectation of g of capital X1 to xn goes to 0 by zeroing 3.4. Expectation of g of xn, that's the expectation of n of x minus f of x. And now I use the fn of x from the, well, it's not nice, but I now use the fn of x in the notation from the theorem 3.4, where this was just the kernel density estimate. It goes to 0. To infinity. Since this one, or since this follows by dominated conversion, from that is L1 arrow n of x minus f of x, probability to 0, and the fact that this L1 arrow is less than 2. Which is by Jeffet the same as integral over is 2 times integral over f of x minus fn of x plus the x, which is less than 2 times the integral over f of x dx, which is 2. And because of this, it suffices to show that the g of x1 to xn minus its expectation goes to 0. Hence, it suffices to show x1 to xn minus the expectation of g of x1 to xn goes to 0 on the Schully. And for this I show that the probability that the absolute value of g of x1 to xn minus expectation of g of x1 to xn, that is absolute value is greater or equal than epsilon, that these probabilities are summable, which implies here for each epsilon greater 0, which implies the assertion.
I just wanted to ask, the part with this follows by dominant conversion from, and the first thing is clear, and the second was used to show that the integral is bounded.
Yeah, the second one is shown that the integral is bounded.
So we can.
So you have the dominating function, yeah? It's just a constant, yeah? That's the second part. That's right. Okay, and now I use this McDiarmid inequality. And in fact, my f is now g. and we have to determine the C i's. So I have to look at the g of small x1 to xn minus g of small x1 to xn, where in the i's component I replace xi by xi prime. So let me look at this one, g of x1 to xn minus g of x1 xi prime I minus 1 is here, sorry, xi plus 1 x absolute value, and I want to bound this guy. And x1 to xn and xi prime are real numbers. So you plug in the definition of g, which is just this integral. Then you see the difference of the two integrals is just the integral of the difference. Then you have the absolute value of it, and the absolute value of some integral is the integral of the absolute value of the function which you integrate. So, or it's less equal than, so that's less equal than absolute value of, here we have an absolute value, then I get some fn of x1 to xn. No, fn von x, x1 to xn, sorry. Minus f of x. Minus the same, but this time fn of x, x1 to xi minus 1, xi prime, xi plus 1, xn. And the absolute value dx. And then you use the second triangle inequality. So use the triangle inequality. The absolute value of r minus the absolute value of b. Absolute value of that is less than the absolute value of a minus b. So this minus f of x cancels out. This is fn of x1, x1, xn minus fn of x, x1, xi, minus 1, xi prime, xi plus 1, this one, dx. Now when you look at the definition of fn of x, x1 to xn, that's the sum. And then you see if I replace in the sum xi by xi prime, then only one of the terms in the sum cancel. So the whole thing is basically, the rest of the term cancels out. So there are only two terms left from the sum. That's equality of, and then you get the i's term here left, 1 over n times hn d k of x minus xi divided by hn. From the first sum and from the second sum with a minus, you get the i's term also left, n times hn d k of x minus xi prime hn dx. And then you see the absolute value of the difference is less than the sum of the two absolute values, and k is non-negative. So you see the whole thing is less equal than 1 over n times integral over 1 over h n d, k of x minus xi divided by h n dx, plus the same time term with h xi prime. And then k is the density, and this 1 over h n d, and then the x minus xi divided by h n and divided by 1 over h n d. That's the minus xi. This translates the density, and this one dilatates the density, but still remains the density. So both time you integrate over density. So both integrals are 1. So it's 2 over n plus k density. So our Ci are 2 over n. Then now we can apply the inequality of McDiarmid. Any questions to that point? And that's it. By theorem 3.7, for any epsilon greater 0, the probability that what I want to show is that g of capital X1 to Xn minus its expectation goes to 0. So I look at the probability that the absolute value of this equal to epsilon, and then I can rewrite the event that the absolute value is greater epsilon, that either the difference is greater epsilon or minus the difference is greater epsilon. So that's the probability of g of x1 to xn, expectation g of x1 to xn. Or just the other two way around. Expectation of g of x1 to xn minus g of x1 xn. Okay, epsilon. And now I use theorem 3.7. Point. Both terms are bounded by so I get 2 times an expectation, an exponential term, and it's both times minus 2 point times epsilon squared over I equal 1 to n. Ci squared, and Ci squared is 4 divided by n squared. And now the sum is 4 divided by n, and then you see the whole thing is 2 times e to the power minus n epsilon squared divided by 2. And since this one is summable, because of sum n equal 1 to infinity, 2 times e to the power minus n times epsilon squared half. This is less than infinity for all epsilon greater 0. Because of this, we get the assertion. Okay, any questions? So see, a pretty simple proof as soon as you know that you have to apply McDiarmid using this function. One error. And as you know that the expected L1 error converges and everything is clear. Questions? So next point is to prove theorem 3.7, which will be more complicated. But before I do this, I make 5 minutes breaks for cleaning the blackboard. So I have on my block now 10:27, so I will go on at 10:32. Okay, then I would like to go on with the lecture. For the proof of theorem 3.7, we need the next lemma, which is lemma 3.8. And in fact, the proof is a generalization of the proof of Höfting's inequality. In Höfting's inequality, we derive the exponential moment of the random variable, and here we derive the conditional expectation, exponential moment for the conditional expectation, or conditional exponential moment. However, don't know how to call it. But let me formulate it. Let Z be an RD random variable on some random space, on the probability space. On omega AP. I have V be a R-valued random variable. So measure a function from omega R to RB. Be an R-valued random variables. Let H, function from RD to R, be bounded. Assume for some constant greater 0. That V takes on values on the interval of h of z with h of z plus c. So we have h of z is less than or equal to V is less equal than h of z plus c. Furthermore, I assume that the conditional expectation of V given z is 0. Furthermore, assume expectation of conditional expectation of V of z is equal to 0. And then the assertion is then we have for all s greater 0. The conditional expectation of E with exponent s mal V given z, that's less equal than some deterministic number. It's E to the power s squared times c squared divided by 8. So you have an exponential moment for E, for V, or for S times V, and in fact it's a moment on the conditional expectation. And you don't see at the moment why this is useful, but you will see in the proof. And next we have to prove this, and this is technical proof. So let me look into my notes. It's basically based on the convexity of the exponential function. So proof. Since if I map x to e to the power s times x, then this is a convex function, which is clear because the second derivative is greater or equal to 0. Convex. And now I consider the case that x lies between a and b. We have for a that's equal x is equal b. I look at e to power e with exponent sx, and I rewrite this s times x in a complicated way, and I rewrite it as a convex combination of s times b and s times a, and the weights are x minus a divided by b minus a times s times b, plus the other weight is b minus x divided by b minus a times s times a. Now you can look at this. Well, of course, these weights are greater or equal than 0, and they sum up to 1. Yeah, x minus a plus b minus x minus a divided by b minus a plus b minus x divided by b minus a is 1. And if you multiply the whole thing out, then you see the denominator is b minus a, and in the dominator you have x times s times b, and here you have minus x times s times a. But I wanted to start with the other one. You have minus a times s times b, and you have plus b times s times a, which cancels out. And then remains x times s times b minus x times s times a, and you can move the x times s out, so it gets an x times s times b minus a, which cancels with the numerator. So it's indeed the correct thing. So I have written this s times x in a complicated way as a convex combination, and then you know for a convex function you have the function value at some convex combination of the input is less than or equal to the convex combination of the function values at these two input points. So that's less than x minus a divided by b minus a times e to sb plus b minus x divided by b minus a times e to power sa. So we have this one, and this now I apply with small x equal to capital V. And then this capital V is between h of z and h of z plus c. So I use for a equal h of z. And I use for b h of z plus c. And then we get e to the power s times v is less equal than x plus v, so this v, a was h of z, and b minus a is c, times e to the power s times b, so it's s times h of z plus c, and I multiply already out, s minus c plus s minus h of z. That's e to the power sb plus b minus x. b was h of z plus c. minus x was v divided by b minus a is c times e to the power s times a is e to the power s times h of z. So we have this one. Now what I want to bound is the conditional expectation of e to the power s times v given z. Let's do this. E to the power s minus v given z. If we bound this, yeah, well then we just get this conditional expectation is less equal than the conditional expectation of the right hand side, and by linearity of the conditional expectation, this is less than the conditional expectation of, well, these two, or the sum of the two conditional expectations almost surely. Then this one is measurable with respect to z, doesn't matter. Then you can move the conditional expectation to v, and we can use that the conditional expectation of v given z was 0, and then you see what the whole thing is minus h of z divided by c times e to the power s minus c plus s minus h of z. Because this whole thing here now is measurable with respect to z, plus again this guy here cancels, and I write it in this way. So the conditional expectation of v is again 0, h of z divided by c plus 1 times e to the power s times h of z is again measurable. So we have this one. The only question is, okay, now we are so far, what shall we do with this thing here? It's not obvious that we are any step further towards finishing our proof than when we begin, but it is the case. We rewrite this in a technical way. Now I use minus h of z divided by c I defined by this small p, and this p, that's minus h of z you see, and this one is going to equal 0, since if you look at h of z is the same as the conditional expectation of h of z given z measurability, and we know that the conditional that h of z was less equal than v, so that's less equal than the conditional expectation of v given z, and that was by assumption 0. And with that one we get e to the power, conditional expectation of e to the power s minus v divided by z is less equal than okay, maybe I p times then the e to the power s z, I see we let's get it, and h of z is minus c times p, so that should be minus s times p times c. We got this one, and the h of z plus h of z divided by c plus 1 is 1 minus p e to the power h of z is minus p times c minus s times p times c. This doesn't look better anyhow, but you will see in a moment. Now I rewrite this as where we move out the common factor, which is e to the power minus s times p times c. And then what is left is 1 minus p plus p times e plus c times e to the minus s times p times c. And I rewrite this as e of some function phi of u, which I define below, almost surely, where I claim u is equal to s times c, and my phi of u should be the logarithm of, yeah, you see u is s times c, so you can replace the s times c by u here, and then phi of u is the logarithm of this right hand side, so that's minus pu plus logarithm of 1 minus p plus p. P times e is power. So we have this one. So I want to bound the conditional expectation of e to the power sv divided by z. I have already an upper bound by expectation of phi of u, and what I do now, I derive an upper bound on the phi function by making a Taylor expansion. And more precisely, you make a second order Taylor expansion around 0, and then everything will be clear. That will give us our bound. And p is some random number, but it doesn't matter, because p can be any number greater 0, and u is some positive or non-negative random argument. So I think it's similar to the proof of everything. You also make such kind of expansion moment. You also make some derive some bound, and then using the convexity, and then used the Taylor. And I don't remember whether it was actually the same function phi. Okay, let's start with the Taylor expansion of second order, no, first order, and then bound the remainder. So we derive the derivatives until the second order. What do you know now? Look at this function phi. The p is an arbitrary constant. U is the argument, yeah. What is the function value? Oh no, maybe first we compute the derivative. Phi prime. Can anyone of you tell me what the derivative is? Phi prime of U is I guess you can just get quite sure. Please? Minus p?
Minus p plus 1 divided by what's
1 divided by this whole term.
times
Times the derivative, which is p times exponential u, yeah? Correct. Now we look at the second derivative. Or maybe first we look at what is phi value at 0? It's 0 because you get a 0 here, yeah, and you get here a minus p plus b, so it's just a logarithm of 1 which is 0. What is phi prime of 0? It's also 0, yeah? Because phi prime of 0, this one will be 1, yeah? Then you see the whole denominator here will be 1, so it's minus p plus b is 0. Now we look at the second derivative. What is the second derivative? Well, we forget about the minus b, that's 0, and the other one, we use the product rule maybe. And then you see if you first make the derivation of the second factor, then it's just the same term. So it's p times exponential of u times 1 divided by 1 minus p plus p times use. And then I have to add the product where I derive the first factor and keep the second factor. So just let me write the second factor. It's p times into u. And then the first factor is the function is exponent minus 1, so it's minus 1 times this function squared. 1 minus p plus p times exponential u squared. And then you have to multiply with the inner derivative, and the inner derivative is just p times exponential u. So we got this one. And now we write this a little bit in a clever way. The common denominator is 1 minus p plus b times exponential u squared. And then I have to multiply p times exponential u with 1 minus p plus b times exponential u. So it's p times 1 minus p times p times exponential u plus p squared by a of 2 u. And then I make a minus. Well, from the other one I just get minus p squared times exponential e with power 2u. Then you see the whole thing cancels. And then it's 1 minus p times p times exponential u divided by 1 minus p plus p times exponential u squared. And now the trick is to see that this is less equal 1 divided by 4, because you have here an a plus b squared, and here you have an a times b. And you know that a plus b squared is greater or equal than 4 times a times b, where it's using the binomial expansion. So the a plus b squared is a squared plus b squared plus 2ab. If you subtract from this minus 4ab, then you get a squared plus b squared minus 2ab, and that's a minus b squared, which is straight equals 0. We have this one, with this one we have and 6. Okay. Now we make a Taylor expansion. Using a Taylor expansion. Around 0. And the standard bound for the remainder of it we get what did I want to show you? I want to derive an upper bound of phi of u. And I make a Taylor expansion of order 1, so that's phi prime of 0 around 0 plus phi of 0 plus phi prime of 0 times u minus 0 plus 1/2 times the second derivative at some point between 0 and the argument, which I call sin u times u minus 0 squared. And then you see the first one is 0, the second one is 0, the third one is less equal than 0 plus 0 plus 1/2 times, and the second derivative is at most 1 divided by 4 times u squared, so that's u squared 8. Which implies our assertion here. Yes. Which implies our expectation. E with equivalent S minus V given Z. This was less equal than E with exponent phi of u, and that's less equal than E with exponent u squared divided by 8, and u was S times C, so that's E times S squared times C squared divided by 8, and I think this should be our assertion. Yes. Okay. Got it. Questions? No idea how you find such a proof. But of course somehow it's similar to the Höfting proof. I think you know the Höfting proof, and then you modify it. This one. Questions so far? Yeah. And I have 20 minutes or 18 minutes for 30 minutes proof. Yeah, that's that's how. Well, it's a good thing, yeah. Okay. But you can't change it. Proof of theorems we can say. How to prove this? Well, we had our assumption that our function f, let's do that. I have it here, yeah. we had some, no, I don't have it here. I have it in the diamond inequality. We had our assumption star. We had some function which was from a to the power n to r, which was real valued. And if you change it in any coordinate, then the function values change at most by ci. And now you, well, of course, a has to be non-empty, which is clear because the random variables takes on their value in a. So you take any point in a, then the function values at this point is some fixed real number. And then if you walk away from this point, so if you change any coordinate, then you change at least. So you start with this point. Then in the first coordinate you go to this coordinate where you want to go to in the first coordinate. Then the function values increases by at most ci, c1. Then from this one you go with the second coordinate to the coordinate where you want to go. It increases at most by c2 and so on. So you see you get a bound on the absolute value of the point by at most the original term where you start the function value bounded plus the sums of the ci. So by star you know that f is bounded. By star you know that f is bounded. Now what we want to bound, at least for the first assertion and the second assertion, just follows from the first bound on the, so we had the probability, we wanted to give an upper bound on the probability that f of z1 to zn minus this expectation greater equals epsilon. And then we want to give an upper bound on expectation of f of z1 to zn minus its random variable, its random variable. Is greater than epsilon. So the second bound you just get by replacing f by minus f. So I just look at the first and I define v as z1 to zn minus the expectation of f of z1 to zn. And I introduce some more random variables. That's expectation of f of z1 to zn given z1 to zi minus expectation of the same random variable given z1 to zi minus 1. For I equal 1 to n. And then we have, if you look at this one, if you sum up the v1 v1 to vn, then this is the telescope sum and you end up just with v. Equal 1 to n vn is equal to v. That's the first. First part. And what I have to derive, an upper bound on the probability that v is greater or equal than epsilon. So I have to derive an upper bound on the probability that this random sum here is greater or equal than epsilon. else for any s greater 0. We have we look at the probability which we want to bound f of z1 to zn minus its expectation. That's greater than epsilon. And that's just the probability that v is greater than epsilon. And that in turn was that this probability that the sum of the I equal 1 to n vi is that's equal to epsilon. It's greater equal than epsilon. And now we make Chernoff exponential bounding trick. This sum greater equal epsilon is the same as s times the sum greater than s times epsilon, and then by monotonicity of the exponential function, this event that s times the sum is greater equal than s times epsilon is contained in the event that e to the power s times this sum is greater equal than s times epsilon. Correct. So that's less equal than e to the power s times equal 1 to n vi is greater than e to the power s times epsilon. Since x maps to e to the power s, x is monotone increasing. All the exponential functions monotone increasing, and the multiplication by s doesn't change anything. You got the same arguments. Now you use Markov. Markov inequality. That's less than the expectation of the left-hand side divided by the right-hand side. So it's e to the power minus s times epsilon times expectation of e to the power s times I equal 1 to n. Okay. Now we rewrite this expectation. Okay, what do we have? The VI's are a function of the Z1 to Zn. More precisely, Vi is a function just from Z1 to Zi. Now, I condition on Z1 to Zn minus 1. Zn minus 1. So the expectation is the expectation of the conditional expectation. Now the V1 to Vn minus 1 are measurable with respect to Z1 to Zn minus 1. The functions are bounded, the random variables, because f is bounded, so we don't have any problem with integrability of the functions or products of the functions. So I can use the rules for conditional expectation. we use that I equal 1 to n minus 1. Vi is measurable. Respect to sigma algebra generated by z1 to zn minus 1. So you see I can rewrite this whole thing as a e to the power minus s times epsilon times expectation of e to the power s times equal 1 to n minus 1 Vi times the conditional expectation of e times s times n if we set 1 to zn minus 1. And now the trick is, we will show in the sequel that this conditional expectation e to the power s times en given z1 to zn minus 1, that this is less equal than e to the power s squared cn squared divided by 8. And this we will do by our previous lemma. And as soon as we have this, the proof is finished, which implies our probability which we want to have, that's less than well, we have this e to the power minus s times epsilon, and that's this one was less than this function, e to the power s squared times cn squared divided by 8. And then you have the conditional expectation of e to the power s times some I equal 1 to n minus 1 Vi, we have this one, yeah? And now you just make the same argument with n replaced by n minus 1, then with n minus 1 replaced by n minus 2, and so on. And obviously we get an e to the power minus s epsilon times product I equal 1 to n e to the power s squared times cn squared divided ci squared divided by 8. So basically we show this equation for any n, so it also holds for n minus 1, it holds for n minus 2, and so on. And then you have this bound, then you see the whole thing is e to the power minus s times epsilon plus s squared divided by h times some I equal 1 to n ci squared. Now we choose s in the proper way. S must be chosen as 4 divided by epsilon into n ci bar, ci squared. And then you get an equality even if you plug this in, then you get an e to the power minus 4 epsilon squared divided by the sum and this is plus, it gives you a 16 epsilon squared divided by 8, so it gives you a plus 2 epsilon squared, sum squared times the sum gives just divided by the sum. So you get equal e to the power minus write it here, e to the power minus 2 epsilon squared divided by the sum. With f replaced by minus f, we get also the second assertion. And you see what is left is the proof of star. Where is it? Here, or star star. And that was our, it will be our lemma from the previous one. Okay? Questions so far? Then I finished in time. Maybe 1 minute too long, so maybe you get 2 minutes back on Friday. But that's it basically. Thank you very much. See you on Friday.